end show. And I'm going to pull that definition out and plop it in a notebook. And there it is. Hopefully, somewhere along the way, you've come across the idea of a rate. And whenever we measure rate in the definition of something, we're talking about the change in that the change in that measurement, the change in that whatever it is over time. And acceleration is no different. The rate of change in object velocity. That means that acceleration is equal to the rate of change of an object's velocity. So delta v, change in velocity, over delta t. In order for us to calculate the acceleration, we need to know two velocities. We need to know a final velocity minus an initial velocity, right? Divided over the time frame over which that velocity changes. If we examine this a little bit closer, we'll see that the units that are involved here get a little bit complex. But when you really think about it, the unit is very descriptive as far as what acceleration is telling you. Let's do that real fast. Okay. So, acceleration we learned in the last video is measured in meters per second. The displacement that we go divided by the time over which that displacement occurs. And whether we're talking about an initial velocity or a final velocity, we still have meters per second. So on the top of this fraction, we have meters per second minus meters per second. That's still going to give us meters per second. Hopefully you remember that from your unit analysis from the beginning of this section, or beginning of this class. Time, still seconds minus seconds. If you think about delta t being final time minus initial time, we're still going to measure time in seconds. And that leaves us with meters per second over seconds. If you look at this unit, it's pretty complex, but if you look at what acceleration really tells us, all right, hold on one second, let me grab that. This is going to probably take a little bit longer than, for your viewing pleasure, but hopefully it will help. Edit, paste. What acceleration is really telling us? Acceleration tells us how much velocity changes each second. So if the unit for this is meters per second over seconds, or meters per second, that's really what it's telling us. Meters per second, how much does the velocity change every second? Now, this is a pretty complex fraction, and because of that, a lot of times we don't write it this way, even though it might be the most descriptive. Sometimes you'll see it written this way, meters per second, although I don't really like that because it's kind of like three fractions in a row. I don't know, it just looks weird to me. But most often what you'll see is if you do a little rearranging of this fraction, right? If we have a complex fraction, we'll try and get rid of the bottom. In order to get rid of the bottom, we're going to multiply the bottom of that fraction by 1 over s. That's going to make my s's cancel on the bottom. But if we multiply the bottom of the fraction by 1 over s, got to multiply the top of the fraction by 1 over s to keep it the same fraction, and therefore we end up with meters per second squared. That's the unit that you're going to see most often on acceleration. But more importantly than what it's measured in is this part here. Acceleration tells us how much velocity changes every second, or how much does the velocity change over time. And that's really what the answer to that third question, what will the object be doing in the future, measures. How much is it changing? If we know how much it's changing, then we can look into the future and go, okay, if it's changing a certain amount in this time, if I know it's 5 seconds from now, I should be able to predict what that velocity is going to be at that time. In order to further illustrate that point, we're going to take a look at these pictures. So it says, describe the motion in the following diagrams. Here's the first two. In letter A, I think that most of us could get to the point where we look at that and go, you know what? That object is standing still. It's not doing anything. And that's correct. It isn't doing anything. if you look at the motion diagram in letter B, if we say that this is some kind of like a stop motion picture where they took a picture at regular intervals, so regular time intervals, and we saw this person at this spot at time A, and this spot at time B, and this spot at time C, and this spot at time D, I think we would look at that and go, okay, she's moving at the same displacement for each time interval. She's moving the same displacement in each time interval. I think most of us would be able to say that, okay, that should be a constant velocity, that she's moving at the same rate over time. With that in mind, with that in mind, if we get rid of the shade and look at letter C and letter D, in letter C, we look, if each picture represents an equal time interval, the same amount of time, if we look at picture C, the distance keeps increasing in each equal time interval. This is an object speeding up. She keeps going farther in each consecutive time interval, or each equal time interval. Then, in letter D, we see that this space, once again, pictures representing equal time interval, this space keeps getting smaller and smaller and smaller, representing that she's going less distance in each time interval, and hopefully that's slowing down. What we want to do now, though, is let's take those same four pictures and let's put them in terms of these words that we're using to describe the motion, namely velocity and acceleration. Velocity being what's happening now, acceleration being what's going to happen in the future. So for letter A, right, object is standing still. If we look at her displacement every second, we would say that the displacement is 0. Remember our definition of displacement being the change in position, right? Where did she end up versus where did she start? Well, she keeps ending up in the same exact place where she started. So that displacement is going to be equal to 0. So we would say that this velocity is equal to 0 in this case, or she's standing still, 0 velocity. Remember, though, from the previous page that our definition of acceleration being how much is the velocity changing over time? Well, this velocity isn't changing at all. So that means that her velocity is 0, but she also has a 0 acceleration as well. No velocity, no acceleration. That's going to be a constant velocity. Okay? In the second picture, remember we talked about the idea that if each of these pictures represents an equal time interval, the displacement in each time interval keeps being the same, right? If we say that this is the displacement in each time interval, right? And then we take that displacement and go boom, boom, boom. It's the same displacement every time interval. That means that her velocity, displacement over time, is going to be constant. There is no change in the velocity of that object. It's the same velocity over and over and over again. But if we look at it from an acceleration standpoint, remember acceleration tells us how much the velocity changes, right? Going back to our definition of acceleration, A is equal to delta V over delta T, right? Here, that velocity is constant. There is no change. So that means that our acceleration is going to be 0. We can have an object moving without it accelerating. Remember acceleration being the change in velocity. Something moving with a constant velocity is going to have a 0 acceleration. Let's take a look at picture C and picture D now, because these get a little bit more complex to analyze. So I'm going to take this and scoot it up to the top so it gets out of the way. All right, picture C and picture D. We said that in picture C, it looks like she's speeding up, right? She keeps going a farther displacement in each consecutive time interval. And if we want to illustrate that point again, right? Here's the displacement in the first time interval. If we then move that to the second time interval, right, she's gone farther than that. And then in the third time interval, she's gone even farther. And in the fourth time interval, she's gone even farther. Her displacement keeps getting bigger for each consecutive second. So in this case, we would say that her velocity is increasing, right? Oh, that's a C. It's supposed to be a C. Velocity increasing. Now let's look at acceleration, because this is where it gets a little tricky, okay? So acceleration, we said, was equal to delta V over delta T. And that means it's V final minus V initial over the time interval during which that change occurs. Okay? If we look at this picture in general, right, her final velocity, which would happen like, I don't know, let's say here, okay, the last picture, however fast she's going at that point, because we said that her velocity is increasing, her final velocity has to be greater than her initial velocity, whichever was, or however fast she was traveling back here at the beginning. So if we plug a final value that's greater than an initial value into this equation right here, this top of the fraction is going to turn out to be a positive value. So that means that when we plug this into the equation, and we mentioned in the previous video, if you ever have time that's negative, you have a real big problem. So time should always be positive. But if you have a V final that's greater than a V initial, the top of this fraction should come out to be a positive number. So that means that she is experiencing a positive acceleration. Okay? But if we go back to this, if we look at picture D, right? Here, velocity is decreasing, right? Sorry, C, decreasing. If we look at that same equation for acceleration, right? Delta V over delta T, which we can calculate as V final minus V initial over the time interval during which that occurs. Here is her displacement in the first time interval. If we take this displacement and look at it in the second time interval, she's gone a much smaller distance in that second time interval than she did in the first, or she has a smaller displacement during that second time interval than the first. Same thing with the third, and same thing with the fourth. Velocity is decreasing. So if we take that and look at her velocity at this point in time, the final velocity, it's smaller than what her velocity was originally. If we plug in a velocity final that is smaller than a velocity initial, the top of this fraction is going to turn out to be negative. Time should always be positive, so if you end up with a negative value on the top of the fraction and a positive value on the bottom of the fraction, her acceleration turns out to be negative. Now, keep in mind, acceleration is a vector quantity, much like velocity and displacement and position. It has both magnitude and direction. Negative velocity negative acceleration means that the velocity generally is getting smaller, although we'll see that that's not always the case, and it kind of really depends on our frame of reference. But in this case here, decreasing velocity, negative acceleration. There's one point that I want to make on this, or a couple of things, summarizing this up. Okay? First, acceleration is defined as any change in velocity over a time interval. And that can encompass three things. First, things that are speeding up are acceleration. And generally that's what we think of as acceleration. But according to the definition of acceleration, the change in velocity over time, there also can be other motions that can be considered acceleration. Like we just saw, slowing down is also acceleration. It's negative acceleration, but it's acceleration. The third thing that can be considered acceleration, and we haven't really talked about this at this point in time, is changing directions. Remember, velocity is a vector quantity, so it depends on magnitude and direction. If acceleration measures the change in velocity, if we've changed direction, we've changed velocity. We'll get into that way more when we talk about like circular motion and stuff like that. But at this point, from a conceptual standpoint, if you change directions, you change velocity. Calculating the acceleration is a little bit more complex in that case, and we're not going to do it now. But it is a change in velocity. Therefore, it fits the definition of acceleration. Last thing as far as acceleration goes. Oh, sorry. That there. Okay. This is sort of a pet peeve of mine, but something to keep in mind. Okay. Slowing down is not deceleration. Okay. That is not a physics word. The physics word to describe a changing velocity is acceleration. It can be positive, it can be negative, but it's still acceleration. Therefore, let's not use deceleration. If we're discussing slowing down, let's call it negative acceleration, because that's what it really is. Next, what I want to show you is a couple of real live examples of how we get these values and what does it mean if we have a positive acceleration and a negative acceleration, and we'll do that in just a second.
To illustrate those points about the positive and negative acceleration and what kind of motions correspond to those types of accelerations, I set up a little ramp here. Just set up a couple of books down on the other end. Motion detector already clicking. Pass car just going to roll right down the ramp. But what I'm going to do is, as I show you this object sliding down this ramp, you should probably hear the motion detector in the background clicking. I'm going to take some data, and then we're going to come back and analyze that data up on the screen so you can actually see some of these numbers and see where it's going and what it's doing and how these values correspond to one another. So all I'm going to do here is I'm going to take it up about halfway, or take the car about halfway up the ramp, let it go, let it come down, let it bounce off of the end, and then finish data collection, and we'll show the analysis of that data collection there. Okay? So stand by, let me get my lab quest ready to go. Okay. I'm going to take this up about halfway, and then you should hear some clicking here in a second, and I'll let it go. And there we go. And in just a second, I'm going to show you the analysis of that data up on the screen. Stand by.
Up on the screen, you can see 4 different screenshots that I took of the lab quest showing data from this cart at different points in time. I just want to use these 4 shots here to illustrate or further illustrate some of those concepts that we conceptually talked about when we looked at the motion diagrams of what it means for positive acceleration, what it means for negative acceleration. But first, we have to keep in mind, right, let me do this, let me scoot my picture over a little bit, that acceleration we defined as delta V over delta T, the change in the velocity over the time period during which that change occurred. So, real generally, there's the graph, right? It's the same graph each time, but if you look at, on the lab quest, I took different data points there, and over on the right-hand side of the lab quest, it gives me the values of both the velocity and the position at that particular moment in time. So here, on the 2 top pictures, and when I do this, so we just focus on the 2 top pictures at this point in time. These 2 top pictures are taken from this gentle increasing slope of the velocity graph. And hopefully from math class we realized that if we're measuring velocity on the y-axis and these values keep getting bigger, 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 this is the part where that cart was speeding up as it went down the hill. Velocity keeps increasing and increasing and increasing. So when we look at the values, right? First, we start with our definition, right? Delta V over delta T, or the final minus the initial, divided by the time over which that occurred. I'm going to change pen here just a second. So, if we look at the values that we actually got from the graph, this value right here, this is the higher up value, the moment in time that's farther, it's, a farther time value. So this will be our final value. If I look at my lab quest, I find out that the velocity was 0.588 meters per second at that second time at that second data point that I'm looking at, minus the initial value that I just randomly picked, where the velocity was only 0.185 meters per second. All of that over the time frame, or delta t, during which that change occurred. So the final time value was 1.30 seconds minus the initial time value, which was 0.80 seconds. I run all of that through my calculator, and I'm going to do that off camera so you don't see me doing that, but 0.588 minus 0.185 divided by 1.30 minus 0.80. Apparently I typed in something wrong. 0.588 minus 0.185. How do I know I typed in something wrong? I got a negative time value. And hopefully we remember that that can't happen. And I end up with, hold on one second, gotta get my pen, 0.806. Hopefully you remember from our discussion before, meters per second over seconds as far as our unit for acceleration goes. What is this saying? That for every second that goes by, that velocity is going to change by 0.806 meters per second. More generally, we write this as 0.806 meters per second squared. Okay. If we focus on another part of the graph, namely this part here, where that blue velocity, where the blue velocity graph takes a sharp dip downwards. And more importantly, it's sharp dipping downwards towards zero, towards the x-axis. Hopefully from math class, because you know graphs and what they're telling you and stuff like that, you could reckon that, all right, that means that the velocity is decreasing as I'm getting closer and closer and closer to zero. We're not going to worry about this part where it goes past the x-axis. That's an advanced skill. We'll get there. But right now, let's just focus on this section. We do the same analysis that we did for the first part. So the acceleration being equal to delta v divided by delta t, or v final minus v initial all over t final minus t initial. Now I didn't write that before, but hopefully we get the idea that delta t is a change in time, and to do that we calculate final minus initial. So once again, we go back to our graphs, and I picked this point right here where in this case here, this will be the initial velocity, because this velocity occurs at an earlier moment in time than this velocity over here. So if I want my final velocity, I have to come over to this graph. So the final velocity in this interval that I picked is 0.129 meters per second, minus the initial velocity in the interval that I picked of 0.573 meters per second. Put that all over the time frame over which that occurs, t final. The time frame that the final time during the frame that I picked, 1.65 seconds, minus the initial time, 1.60 seconds. So once again, go to my calculator, plug these numbers in, 0.129 minus 0.573 divided by 1.65 minus 1.60. Let me make sure that's right. It was, sorry. Didn't have to do that again. You can't see me doing this, but that's all right. Divided by 0.05, and we end up with a negative 8.88 meters per second over seconds, which we said, right, simplifies down to negative 8.88 meters per second squared. So once again, we see here that the velocity, or sorry, the acceleration being a positive value leads us to a speeding up effect, right? In this case, the positive acceleration resulted in an increase in velocity. But here the negative acceleration resulted in a decrease in velocity. And hopefully you can see that the negative acceleration is approximately 10 times larger than the positive acceleration. That means, right, we said that our definition of acceleration is how much does velocity change every second, right? The velocity is changing much quicker in the slowing down portion of the graph than it is during the speeding up portion of the graph. And the acceleration values reflect that. So just to wrap this up, okay, acceleration is a vector quantity. It has magnitude and direction. It depends on velocity, which is another vector quantity, so it kind of makes sense. And acceleration tells us how the velocity is changing, but it doesn't always have to be in the same direction as velocity. For example, if we take a look back at these calculations, right, these are both positive velocities. Remember that from our discussion about velocity, the sign on velocity tells us the direction that that object is moving, but not necessarily how big or small it is, the negative value or positive value at least. These are positive velocities. Why? It's still moving in the same direction, but certain times we have a positive acceleration resulting in a speeding up in that direction. But certain times we have a negative acceleration. Because the velocity is still positive, we're still moving forward. As that cart was bouncing off the block, it's still moving in the forwards direction or down the ramp, right? But as it's moving in that forward positive direction, it's slowing down. And that's what the negative acceleration is telling us. The velocity tells us what it's doing now. Still moving forward, positive velocity. The acceleration tells us how is velocity changing. The negative acceleration showing us that it's slowing down. So, wrapping this up, I'm going to skip this. I'll go here, right? Acceleration tells how velocity is changing. It doesn't always have to be in the same direction. If we have acceleration and velocity that have the same sign, if either they're both positive or both negative, that results in a speeding up effect. In this example in particular, we looked at two positive, or a positive velocity and a positive acceleration, which probably makes more sense conceptually to you now. But in class, we can illustrate the fact that it will also be the same effect if we have a negative and negative acceleration. But if acceleration and velocity have opposite signs, if one's positive and one's negative, that results in a slowing down. In the case of the lab quest that we just looked at, positive velocity, because it was still moving down the ramp, but negative acceleration resulted in the slowing down. Just to summarize it all up, how the positives and negatives on acceleration and velocity go down, I have this chart to help you, right? Telling you if you have a certain initial velocity, and this is just sign, right? Remember, the sign on velocity is just telling us direction. And then the sign on acceleration determines what physically is going to happen to that object, right? If we have positive and positive velocity and acceleration, we get a speeding up effect. If we have negative and negative acceleration and velocity, once again, a speeding up effect. However, if we have a positive velocity and negative acceleration, or a negative velocity and a positive acceleration, we get a slowing down effect. But regardless of what the velocity is, if we have zero acceleration, constant velocity, no change in that velocity. Hopefully this clears up, or at least introduces you to those concepts of acceleration. We'll deal with them conceptually, what they mean to the motion of the object, how we calculate that velocity, way more in class.